My talk will be without gas. It's on a vacuum discharge, and it is about a model of explosive electron emission plasma parameters. If you have no gas but still want to transfer current, we may use explosive emission pulses at the surface that may provide plasma flare and media for transfer current in Boylan style manner. It is known that this dense plasma with fast time in the second time range, and it decreases from solid state density to normal density when expanding outwards from the cathode. So there's some challenges with modeling of this phenomena. It's fast, it's local, and there's apparent interaction between previous explosions and further explosions. This is a model. This is a model of liquid metal jet tearing and explosions. So we know that there is some liquid metals that interact with plasma and provide. We think that it provides further explosions. So we have a model with expanding of liquid metal jet into the plasma from previous explosion, and due to tearing, hydrodynamic tearing of jet, we may get explosion of this neck, and we have proposed a model of transition from critical state. So the jet temperature rises to the ohmic Joule heating up to critical temperature, and the critical state is when we reach critical state, there is no cohesive energy, so we can freely expand the matter, the plasma from this point. So the parameters of critical state is about 1 eV in temperature and almost solid state density. And also we have, due to non-ideal plasma, we have strong reduction of energy potential. So it's not a media, but in metal we have plasma just at this point. So we have we catch three main parts of the elephant. So there is ignition of the pulse from due to tearing, transition over critical state, and expansion outwards is extinction phase. It follows from this model that the velocity of plasma expansion is about ion acoustic velocity for the ions and for the given critical temperature. And indeed, we can see agreement with the measurements of plasma flare expansion, anomalous ions velocity, represented here, and it's nearly about 10 times larger than ion acoustic velocity at the expansion. Another point is ionization state. We can estimate it by average charge in this formula with a reduction of ionizing potential due to non-ideality. And for the dense plasma, which is about, we know that it's about 10 in 20 per cubic centimeter of the density, and for such a plasma we can get an estimation of average charge, which is T in electron volts, temperature in electron volts, and it will be used further. However, this temperature of electrons changes in time, and due to fast time, it's about nanosecond or below. There is no relaxation between the electrons and ions, and we should use both equation for temperature, so separately electron temperature and ion temperature evolution considered here. So we can see here Joule NGLEs, energy exchange term, and expansion, cooling due to expansion. Again, we use this equation for the neck. So because before the reaching of critical state, critical temperature in ion component, we have construction of the jet and increase in the current density, and after that we have expansion and cooling due to this expansion. We can see that indeed there is no relaxation in our case, so it's sub-nanosecond times, and the electron temperature is somewhat higher than the ion temperature, and we can get approximation with 1 eV plus critical temperature for the maximum electron temperature due to transition through the critical state. And after that, we can use it for estimation of average charge, and so we can get this formula, very simple, and nevertheless it reproduces measurement trend of the material, and also the value is very close to the measurements. And also we can use it for explanation of recent experiments with linear correlation between average charge and ion kinetic energy from its work. From our model we can propose this estimation, which is based on the critical state model of the explosive plasma. Another important thing is momentum of this plasma per transfer charge. This value is also known as recoil force or Tandberg force, but in fact it's not force, it's momentum, because we have pulses, not continuous drag force, something like this. And it was proposed, this value was proposed for the momentum, and unknown, average charge was unknown. And now we can use our results and improve it, and generally we can propose a very simple estimation, which is in fact 5 product square of atomic mass. Very simple, very general estimation, and it agrees with the measurement with very large spread, in fact. So these measurements of ion velocity and erosion rate. So this product of ion velocity and erosion rate. And I'm sorry for large text, a lot of text. This is about cohesive energy rule. So-called cohesive energy rule explains what is the cathode fall in vacuum arc, and we propose that we should use not the cohesive energy, which is vanished due to the transition of the critical state, but instead of this we should use critical temperature. It's about 5, cohesive energy is about 5 critical temperatures, and maybe it's more accurate for description of correlation of cathode fall and parameters of materials. Also we can propose effective critical temperature for microstructure. In particular, this was recent experiments with deviation from the cohesive energy rule, and this deviation may be due to reducing of the critical temperature, because this was some composition of materials, and with some fine structure. This fine structure may reduce this. Basically, you can see lower energy of ions and a lower perturbating voltage. So we can propose that effective critical temperature can explain this. So our model, besides its simplicity, it considers Sakhalin equation for average charge for weakly non-ideal plasma. It considers two temperature calculation with finite relaxation time between electrons and ions in metal. And the current density evolution was given by T and jet model. So it's not given by some assumption, is more it's more towards to the real condition, as we suppose. And after work was published, there was some additional considerations, and probably we should use not the critical temperature for estimation of plasma parameters, but plasma parameters for estimation of critical temperature, because in fact for most of materials there is no measurement of critical temperature. Because, for example, estimation for tungsten gives about 1 eV. So solid state media with 1 eV temperature is extremal states and hardly can be measured at all. And we can propose a plasma tool for estimation of critical parameters of the material. Thank you very much.